Hello, today we're going to talk about reactivity 3.4.8. This is an HL only topic, and it's all about coordination bonds or coordinate bonds that are formed to make complex ions. So complex ions form between a transition metal ion. I'm going to use TM for transition metal, and I'm going to use just a positive sign, but know that it could be other charges. It could be +2, +3, +4, whatever the charge is. And so that's our transition metal ion is going to interact with a ligand, and typically the ligand will have an additional lone pair of electrons, and it will form a complex between them. And that transition metal will form a coordinate covalent bond to the ligand, and that charge will still be on the overall complex. So the transition metal, because it is positive, it can act as a Lewis acid and accept electron pairs, which means it also makes it an electrophile. The ligand, because of it has those extra lone pairs or extra electron density, is going to be acting as a Lewis base, donating an electron pair. And so it also acts as a nucleophile. And so when those electrons are shared effectively, forming the new coordinate covalent bond, you're forming this new complex. So this is a coordinate bond, and the overall thing is called the complex ion. So an example of something like that would be like CuH2O6. So water, because the lone pairs on the oxygens, the water molecules can complex to the copper ion. And the overall complex has a charge of +2 because the copper ion itself had a charge of +2 and water is neutral. So that's kind of how that works. And so because there are 6 water molecules, there are 6 coordinate bonds to that copper ion, which is in the center. So some really common ligands that you'll see that are neutral are water, which we just talked about. You'll also see ammonia because it has that lone pair as well. And you might see like carbon monoxide or just because there's a bunch of lone pairs on those. Those will complex with a positively charged transition metal ion. You'll also see anions, negatively charged ions. And so you'll see like iodine, bromine, chlorine, fluorine ions, all -1 charge ions. You'll see like hydroxide sometimes. You'll see thiocyanate sometimes, or just cyanide sometimes. All of those will have a -1 charge and will offset the positive charge of the transition metal. So I do want to give you another example. Let's say I have like chromium with 4 ammonias and 2 fluorides, and the overall charge on that is +1. Well, in this case, the ammonia are neutral and the fluorides are -1. So, but there's 2 of them, so that's -2 overall. In order for the overall to add up to +1, that means the chromium must be +3. And this works whether you're talking about oxidation state or charge. So the charge, you'll just make sure you write the charge as the sign after the number when you're doing charge. Okay, so let's talk about coordination number. Let me go ahead and draw one of the coordination complexes. I'll keep it pretty straightforward. Let's do this one here. Okay, so that's the complex. And there's 6 chloride ions attached to the central copper. So they will orient themselves in a way that is octahedral around that central copper transition metal ion. And because there are 6 coordinate bonds around the central carbon, we say that its coordination number is 6. Now, it could also be 2. If the coordination number is just 2, then it's linear. And then if it is 4, then it could be either tetrahedral or it could be square planar. But they would have to give you some other information for you to know which one of those two it would be. So depending on the central atom, the number of coordinate covalent bonds gives us the coordination number. And from there you can get to the Vesper shape of the structure. Just rewrite this so it's neater. Octahedral. 2 is linear, 4 is tetrahedral or square planar, and 6 is octahedral. So let's look at some examples then. Determine the charge and give the formula for the complex ion formed when Fe2+ coordinates with 2 waters and 4 chloride ligands. So our complex consists of iron, 2 waters, and 4 chlorines, like this. Now for the charge, the Fe, they told us, was a 2+ charge. Water is neutral, and chlorine is -1. And there's 4 chlorines, so that's -4 overall. So that means our total charge is 2- for the entire complex. Now working backwards, determine the charge on the central chromium atom in this complex ion with 2 water ligands and 4 bromines. With the -1 charge overall. So that means whatever the chromium is, plus 0 from the waters, plus 4- from the 4 bromines, has to add up to -1. So in order to make that true, the chromium must have a +3 charge.